Good morning, dear students. My name is Ferhan Mazher, and the subject we are studying is today is Cambridge O levels Physics 5054. Today we have set our hearts to solve a theory paper, and we have selected May June 2022, and it's paper 22. This paper 2 belongs from the zone 2, and this is my second video on this paper. In my first video, we have solved the section A of this paper. And in this video, in this session, we are going to attempt the section B of this theory paper. So let's start today's paper. And here we go. Okay. So this is May, June 2022. The section B of this paper is showing up on your screen. And you can see it says figure 7 point, question number 7. Figure 7.1 shows the speed time graph for a car traveling on a straight horizontal road. So it's a speed time graph. Here you have the y-axis. On the y-axis, we have speed. And here you have the x-axis. On the x-axis, we are representing the time. The time is in second. The speed is in meter per second. And here you can see the car has accelerated uniformly up to, I think, it's like 9, maybe 10, up to 10 seconds. From 0 to 10 seconds, it has accelerated uniformly. And from 10 seconds to 20 seconds, it has moved with a constant speed of 16 meter per second. From 20 seconds to 24 seconds, it has decelerated and its speed has changed from 16 meter per second to 0 meter per second. So this is that graph. He says, describe the motion of the car. It's a 3-box question. So I have already described it. You see, the car started from the rest, and from 0 to 10 seconds, it accelerated uniformly, and its speed changed from 0 meter per second to 16 meter per second. From 10 seconds to 20 seconds, for these 10 seconds, the speed of the car remains constant at 16 meter per second. From 20 seconds to 24 seconds, the car decelerated uniformly, and the speed of the car changed from 16 meter per second to 0 meter per second. So this is how you will describe the motion of this car. And here we go. Let me show you my written answer. So from 0 second to 10 seconds, car has accelerated uniformly from 0 meter per second to 16 meter per second. From 10 second to 20 second, car traveled with constant speed of 16 meter per second. From 20 second to 24 second, car decelerated uniformly from 16 meter per second to 0 meter per second. So it's a 3 marks question. So let me show you the marking scheme. The question number 7 is first part. These are the 3 marks. And you can see, and we have written the whole thing. I hope you understand. Okay. Now he says, using the figure 7.1, calculate the distance traveled by the car during the 24 seconds of its motion. Show your working. You know the distance traveled we can calculate from the speed time graph. Very simple. You have to find out the area under the speed time graph. So area under the speed time graph, this is a trapezium. And if you have studied in your mathematics, the area of the trapezium is 1/2 into height into sum of parallel sides. So the height of this trapezium will be 16. This side and this side, they are parallel to each other. This side is 24. This side is 20 minus 10 is 10. So I can apply the formula and I can find the area under the speed time graph, and that will be equal to the distance traveled. Okay. So distance traveled will be equal to the area under the speed time graph. And that shape is a trapezium. So its formula is 1/2 into height into sum of the parallel sides. And that will be 1/2 into 16. And in the other bracket, you will have 10 plus 24. The upper side is 10 and the lower side is 24. So you will have 2 and 16 will be cancelled. So you will have 8 into 34. And that will be 272 meters. So the distance traveled is 272 meters. It's a 3 marks numerical. So it will be 272 meter. Okay, so our answer is right. Okay, the next question coming up on your screen, he says, calculate the average speed of the car during its motion. You know, if you want to find out the average speed of a journey of a car, of its journey, we can find it very simple. The average speed is equal to the total distance traveled by total time taken. We know the total distance traveled, we know the total time taken, so we can find average speed is equal to total distance divided by the total time. That will be 272 meter divided by 24 seconds. And when you divide them, the answer will be 11.3 meter per second. So 11.3 meter per second is the answer, sir. So let's have a look at the marking scheme. 11 meter per second is the answer. They rounded off. They rounded it off to the two significant figures. So our answer is right. Okay, so the next question they are asking is, a second car travels at a steady speed. It travels the same distance as the first car in the 24 seconds of the journey. On the figure 7.1, draw the speed time graph for the second car. Okay. For the second car, I will draw the graph that covered the it covered that distance in how much time? 24 seconds, but that car moved in on a steady speed. So the graph will be a straight line, straight horizontal line, but I don't know how much will be its speed. The graph will be in the shape of a rectangle. So the area of that rectangle will be equal to the distance traveled. So the length of that rectangle will be the time taken. We know that 24 seconds, but I don't know what will be the speed. That will be the width of the rectangle. So length into width is equals to 272. So length is 24 multiplied the width equals to 272. So the width will be 272 divided by 24, and that will be 11.3. So the speed of the car should be 11.3. So on the graph paper, I will draw a line, horizontal line, 11.3 at 11.3 speed, and it will be horizontal line up to 24. So this is the graph for the second car. This is what they were asking, this graph. Okay, this graph. I hope you understand that how we have done this. The thinking distance is the distance traveled by a car between the time that a hazard is seen and the time that the brakes are applied. The braking distance is the distance traveled while the car slows down to rest. Table 7.1 shows the thinking distance and braking distances of an alert driver when the car travels at different speeds. So when the speed is okay, when the speed is 20, the thinking distance is 9 meter per second. The braking distance is 2 meter. Sorry, I said meter per second, it's meter. When the speed is 40, the thinking distance is 18 and the braking distance is 9. When the speed is 60, I don't know what is the thinking distance, and the braking distance will be 20. When the speed is 80, the thinking distance will be 36, and the braking distance is also 36. When the speed is 100, the thinking distance is 45, and the braking distance is 56. Complete the table 7.1. So when you double it, this also doubles. When you give it an increment of 20, here you give increment of 20, here you give the increment of 20. So there's an increment of 9, here again increment of 9. So if I add 9 in 18, it will be 27. So this is how you will. So I'll write here 27. When 20 is added, 20 is added, 20 is added, 20 is added here, in 9 is added, 9 is added, 9 is added, 9 is added. Very simple. Okay. So this is the answer. Here you go. Okay. Now you see, it says the time it takes for the driver to react to the hazard is constant at different speeds. Explain how the table shows this. You see, here the speed is given, the distance traveled during the thinking distance. The thinking distance is given. If you divide the thinking distance with the speed, you will get the reaction time. So divide 9 with the 20, divide 18 with the 40, divide 27 with the 60, divide 36 with the 80, divide 45 with the 100. So every time you will calculate the thinking the thinking time, the reaction time, it will be same. So let me show you here. Here you see my argument is that the thinking time for the first situation, 9 by 20, that will be 0.45 seconds. In the second situation, it is 18 divided by 40, and it will be 0.45 seconds. In the third situation, the distance, the thinking distance is 27, and the speed is 60. When you divide, you get 0.45 seconds. 36 divided by 80, you get 0.45 seconds. 45 divided by 100, you get 0.45 seconds. In all five observations, thinking time or the reaction time is 0.45 seconds. So we calculated actually the reaction time in each case, in each. So I hope you understand this, and let me show you the marking scheme. He says, okay, this is our answer. Okay, so our answers are right. Okay, then the question is, state what happens to the thinking distance and the braking distance when the driver is tired. When the driver is tired, his reaction time becomes larger. So the thinking distance will also become larger. So the thinking distance increase. And the braking distance has nothing to do with the reaction time. It does not depend upon the driver. The braking distance depends upon the braking system. It depends upon the friction between the tire and the road. It depends upon the condition of the tire. So the braking distance will not change, but the thinking distance will become larger. So let me show you my written answer. So it will increase and there will be no change. So let's have a look at the marking scheme. Increase and no change. So our answers are right, sir. So the question number 7, the whole question is almost showing up on your screen. That is the A part. That's the A part of the question number 7 in the marking scheme. This is the rest of the question. So you can pause the video and you can have a look at how this is done. Okay, so now we are going to the next question. The next question coming up on your screen is question number 8. He says, figure 8.1 shows a ripple tank and the crust of the water wave that is produced in it. The frequency of the water wave is 2 hertz and its amplitude is 3 millimeter. Calculate the number of currents produced in 1.5 seconds. I know the frequency. So in 1 second, there are 2 waves produced. When there are 2 waves, the frequency means that how many waves are produced in 1 second. The frequency is 2 hertz, which means that there are 2 waves produced in 1 second. So in 1.5 second, how many waves will be produced? You just multiply 1.5 with the 2 and you get 3. So there will be 3 waves, and in each wave there is 1 crust. So there will be 3 crusts produced. I hope you understand. So in 1 second, 2 crusts are produced. So in 1.5 second, how many crusts will produce? I'm using the method of proportionality. So x cross multiply x equals to 2 into 1.5, and that will be 3. This is how we will do that. So 3. Our answer is right. Okay, so we are going to the next question. He says the height of the wave is measured from the level of the undisturbed surface of the water. And the height of the wave at one point is 0 at time equals to 0. On the figure 8.2, draw a graph to show how the height of the wave at this point varies with the time. Okay, so first of all, the frequency of this wave is given, that's 2 hertz. I will try to calculate what is the time period of this wave. Okay, so you know that the time period is equal to 1 by f, so it will be 1 by 2, that will be 0.5 seconds. So this wave will be completed in 0.5 seconds. So in 0.5 seconds, one wave will be completed from 0.5 to 1 second. Another wave will be completed from 1 second to 1.5 seconds. Another wave will be completed. At 0, the amplitude is 0. The amplitude is 3. So because in this duration, one wave is to be completed, so half wave will be here, half wave will be in this here. Half wave will be here, half wave will be here, half wave will be here, half wave will be here. The amplitude is 0.3, so put a dot here, put a dot here, a dot here, and dot here, dot here, dot here, dot here, and dot here, and this is then join them with the smooth curve, and you will get this shape. So this is how you will draw this graph. This is the mean position. This is showing the mean position of the wave, the the particles of the water. Okay. He says the frequency of the wave is increased, described of the apparatus shown in the figure 8.1 is adjusted so that the frequency of the wave is increased. Okay. The instrument which you are using is this wooden bar and which is hanging with these rubber bands. So if you want to increase the frequency, so this wooden bar should move quickly. It should move faster. So it should move faster up and down. Its vibrating frequency should increase, then the frequency of the waves produced that will also increase. So I think this is the answer. Move the wooden bar up and down faster. Okay. Then they say state what happens to the speed and wavelength of the wave as the frequency increases. If you will increase the frequency, the speed will remain unchanged, but the wavelength will become, what will happen with the wavelength? It will decrease, because when the waves, when your frequency increases, your time period decreases, and if the wave is moving with the same speed, the wave will cover less distance in the same time. So in the time, same duration. So the wave, sorry, I mean the wave will cover less distance because your the time required to complete one wave has decreased. Okay, so that's why the wavelength will decrease. Let me show you. Same, the speed will remain same, but the wavelength will decrease. Okay, the speed depends upon the depth of the water. Okay, so that was the second part. Okay, now let me show you from the marking scheme also. So this is the answer. So our answers are right. And okay, so we are going to the next question. He says C part, the apparatus shown in the figure 8.1 can be used to demonstrate refraction. State the additional apparatus used to demonstrate refraction. To produce refraction in a water tank, we need to decrease the depth of the water, this ripple tank. So we require a glass block which we can put in the ripple tank, and that will reduce the depth of the water in some portion of the ripple tank. So what we need, we glass rectangular block to change the depth. Okay, we need a rectangular block to change the depth of the water. Draw on the figure. The next question they are asking is plastic piece of glass block plate or shallower, deeper area boundary. Okay, so our answer is right. He says draw on the figure 8.3 to show the refraction of the water waves. Label a boundary where the refraction occurs. Okay. For refraction to happen, the glass block must be placed in the water at an angle. So this black line, you can see this. Sorry, I said black line. This blue line, can you see that? This blue line is basically that glass. So the water here is shallow, the water here is deep. These blue color lines, I have shown the water wave fronts. They are going in this direction. This blue line shows the direction of the water waves, wave fronts. And when it touches the boundary of that, where after which the water will become shallow, at that point of incidence, I draw this dotted line, which is normal. Normal means it's making 90-degree angle with the surface of the block. And when the water waves enter from deep water into shallow water, their speed decreases. That's why they will bend towards the normal. And you can see this blue line. I have shown that the wave fronts, they will their direction, the direction of the waves, that will bend towards the normal. Okay, then I will here you see I will place Let me reduce the size so you can see that. Okay, then I will place my protector in this way that the 90 of the protector is on that direction in the shallow water. And when this straight edge of the protector coincides with this the point where this wavefront touches the boundary, I will draw a line here. Then I will move it to the left further, but I will make sure that this 90-degree line remains on this direction line. And when it coincides here, I will draw this line. So this is how you will draw these wavefronts. So it's a bit difficult task to draw the refracted wavefronts. I have done a video in which I have explained how these wavefronts are made. You can find those videos in the chapter of waves. I have made that video. So I hope you understand how this is done. Okay, so here we go. So the question number 8. Okay, now still it's going on. Okay. So the question number 8, let me show you the marking scheme. So we are here. Okay, so we are done, it's good. So you can check it from the marking scheme as well. Figure 8.4 shows a connection to the internet made from a remote station A using a satellite above the Earth's surface. Data is sent between the station A and the B using the microwaves which travel to and from the satellite. Station B is connected directly to the internet using optical fiber. So there's another option. You can directly connect the B and the A by the optical fiber. The speed of the microwave is 3 expo 8 meter per second. Station A and B are each 360 kilometer from the satellite. Calculate the time taken for the data to travel from the A to B using microwave. So from here, 560 kilometer, and from here to here, 560 kilometer. So the total distance traveled, will be 1,560 plus 560. It will be 1,120 kilometer. And but you know the speed given is in meters per second. So I will convert this kilometer into meters. For that, I will multiply it with the 10 raised to power 3 expo 3. So when you divide 1120 expo 3 divided by 3 expo 8, so your answer will be 3.7 expo minus 3 seconds. So it will take 0.0037 seconds. 0.0037 seconds is the right answer, sir. So, okay. Then the question is, the same data can be sent from A to B in a shorter time along the surface of the Earth using infrared waves to carry the information in the optical fiber. State one property that infrared waves and microwaves have in common. You see the infrared waves and the microwaves, they both are transverse wave. They both travel with the same speed. They all obey the equation of the wave. So I can say both are transverse wave. Okay. There are so many similarities between them. You can write anyone. Okay. It says, yeah. So just one other advantage of using the optical fiber to connect station A and B directly. If you connect them directly with the A and B with each other with the optical fiber on the ground, one advantage will be you don't have to do the expense of the satellite. So you don't have, satellites are very expensive to launch them, and to use them is expensive. So you can avoid the expenditure of a satellite. So no satellite will be needed, so it will be cheaper. So we are done with the question number 8. So my dear students, the marking scheme of the question number 8 D part is showing up on your screen. I can show you the whole marking scheme of the question number 8. You can pause the video and you can take your time with the question number 8. So here we go. Okay, so we are going to the next question. The next question coming up on your screen is question number 9. He says thorium-229 is a radioactive isotope used in several medical applications that involve alpha particles and beta particles. During the ionization of the helium atom becomes a helium ion. Figure 9.1 shows a diagram of helium ion. So helium ion is here, you can see it has 2 neutrons, it has 2 protons and 1 electron in it. State how the structure of the helium atom differs from the structure of the helium ion. So in the helium ion, there is 1 electron in the orbit, and in the helium atom, there will be 2 electrons in the orbit. So that's the difference between them. Okay. So here we go. Helium atom has 2 electrons in its orbits. Helium ion has 1 electron in its orbits. Okay, so that's the difference between them. I can show you from the marking scheme as well. Okay, so that is the first part. Okay, so the second part is a state how the structure of an alpha particle differs from the structure of the helium ion. In the alpha particle is like the nucleus of a helium. It has 2 protons, 2 neutrons only. And in the helium ion, it has 2 protons, 2 neutrons, but it also has an electron in its orbit. So the difference between them is of electron. Alpha particles have no electrons, while helium ion have 1 electron in its orbit. In orbit, you can say. Okay, so this is the second part. Okay, no electron, positive charge. Yeah, that's also the difference. Okay, a nucleus of thorium-229, 9229 decays by alpha emission to one nucleus of element X. The nucleus of X then decays to a nucleus of Y by beta emission. Complete the table 9.1 to show the number of protons and neutrons in a nucleus of X and in a nucleus of Y. You see, whenever alpha particle is given out, the proton number decreases by 2 and the mass number decreases by 4. So here it will be 80, 88, and it will be 225. So the protons, number of protons will be 88, and the number of neutrons will be 225 minus 88. So let me show you, and here we go. So in the X, the number of protons will be 88, and the number of neutrons in it will be 225, its mass number minus its nucleon number minus its proton number. That will be 225 minus 88, so that will be 137. Now the X further decays and it gives out a beta particles, and the daughter cell will be Y. So the daughter atom will be Y. So whenever the beta particle is given out, the proton number increases by 1. And the nucleon number remains the same, but the number of neutrons decreases by 1. So whenever a beta emission happens, the proton number increases by 1, the nucleon number do not change, and the number of neutrons decreases by 1. So remember these things. So the Y, the proton number will be more than 1 more than 88, so it will be 89. And its number of neutrons, that will decrease by 1. So before the number of neutrons were 137, and now they will be 136. Okay, so let me show you the marking scheme so you can understand it. So this is the marking scheme of that part. Okay, so we are done with this table. I hope you understand. Okay, so now we are going to the next part. He says the experiment can show that a sample of a material is radioactive. Describe the apparatus and the procedures used to show that a sample emits both alpha particles and beta particles. You may draw a diagram as of the apparatus if you wish. Okay, so this is a 4-mark question. So very simple. You will take a GM tube and you will find out what is the background radiation. Then you will place the sample in front of the GM tube. You will place your GM tube just few centimeters from the sample, and you will note down what is the reading of the radiation coming on the GM tube. Then you will place the paper between the GM tube and the sample, and you will observe that the reading will drop. And there will be a decrease in the reading, which means that some of the radiation was such which cannot penetrate through the paper. So that shows that the alpha particles were present. And because the radiation and the reading, the count rate has not dropped to the background, so it means that it also has some other radiations. Now replace the paper by a sheet of aluminum whose thickness is 5 millimeter. When you will place the aluminum foil, the reading on the GM tube, the count rate, and the radioactive the reading shown on the GM tube, that will decrease to background. It means because the some radiation was not stopped by the paper, so that means that the beta or maybe gamma is also present. But when all the radiation is stopped by the aluminum foil, it means that it has beta particles because the beta particles cannot penetrate through the aluminum foil. But it does not have gamma rays, because if the gamma rays were present, by putting the aluminum foil between the sample and the GM tube, the reading will not drop to the background. So that this experiment shows that the sample is emitting alpha particles and beta particles only. The gammas are not there. So 4-mark question. So let me show you. I have written this answer. So you can see I have made this a lead box, and from here it's open. This is the sample. This is the GM tube. Okay, in front of it. Between them, I can put paper. I can put aluminum foil. So let me show you the reading. What is the read? So use a GM tube to note the background radiation. Put GM tube few centimeters away from sample and note the reading. Place paper between sample and GM tube and note reading. If reading drops, it means it has alpha particles. Replace the paper with 5 millimeter aluminum sheet, and reading on the GM tube will drop to the background radiation reading. This means it has beta particles and no gamma rays are present. So it's a 4-mark question. I hope you understand. Let me show you my, yeah, here we go. So we have the GM tube. We also have I have written this answer, the GM tube answer, and I hope you understand. You can pause this video. Okay. Then he says, state what is meant by the half-life of thorium-229. Remember this definition word to word, average time duration in which half of sample of thorium-229 decays. Average time duration in which half of sample of thorium-229 decays is known as the half-life of the thorium. Okay. So that's the definition. Time taken to halve. Okay. Then their question is, a sample of pure thorium-229 contains 5 expo 14 atoms. After 22,000 years, the number of atoms of the thorium-229 in the sample is 5 expo 13. Determine the half-life of the thorium-229. Show your working, 3 marks numerical. So this is how we do the working. So initially there were 4 expo 14. So divided with the 2, so one half life, they will left with 2 expo 14 atoms. Further divided with the 2. So after second half life, there are 1 expo 14 left. Divide this number again with the 2, you are left with 5 expo 13. So count how many half-lives have passed. 1, 2, we count the gaps. This is 1, 2, 3. It means after 3 half-lives, the count rate the number of atoms will be how much atoms are left? 5x per 13. So the total time passed is 22,000 years. So 3 half-lives have passed. So 22,000 divided by 3, and that will be 7,333.33. So the half-life is approximately 7,300 years. So let's have a look at the marking scheme, 7,300 years. So my dear students, by this question, we have reached the end of this paper. So the marking scheme of the question number 9 is, here's the marking scheme. The whole marking scheme for the question number 9 is showing up on your screen. And you can pause the video if you want to take a look at this marking scheme and you want to take time with this marking scheme. So we are done with this question, and so this paper is over. So my dear students, today in this video, we have done May, June 2022 Physics 50542 paper. This paper 2 was from the zone 2, and in this video, I have done the section B of this paper, and this paper is completed. I have already done a video on the section A of this paper, which is already uploaded in my YouTube channel. So you can find both the section A and the section B in the same playlist of my channel. So if you have, if you are watching this video and you have watch this video and you think that this video has helped you and it has helped you to practice the past paper, please share the link of this video onto your Facebook account, onto your Instagram, and onto your Twitter account, because that will help me promote my channel. I think that is a great blessing for me, that God has blessed me with an opportunity that I can help so many students around the world by this YouTube channel. So thank you very much, everyone. Have a good day. God bless you all.